Hello, Professor. I'm TANG YONGQING, and today I'm honored to present my master's thesis, Machine Learning-Driven Housing Price Prediction in Xiamen, a coastal city case study. This research introduced a machine learning framework enhanced with spatial features aimed to predict housing price in Xiamen. By combining attributes with shape, it captured the nonlinear effect of BRT proximity while offering practical guidance for urban planning. The model improves predictive accuracy and brings interpretability to complex spatial relationships. To understand the motivation behind this research, let's first look at the core problem. Traditional models like OLS often assume linearity and overlook spatial dependencies, which limits their performance in urban settings. They struggle with features like proximity to transits and cannot review the varying effects across different districts. This creates a gap between statistical prediction and what policymakers need. In order to address these challenges, the following three research objectives were designed. First, to apply machine learning models to predict housing price. Second, to explore spatial and non-linear effects, particularly around BRT systems. Third, to use explainable AI methods to inform better planning decisions. Recent studies show that machine learning models like XGBoost and LightGBM outperform traditional ones in predicting housing price. Special features like POI density and BRT access also boost performance. Among these models, XGBoost stands out for both accuracy and interpretability through shape. Based on this earlier insight, I developed a methodology that integrates spatial features with machine learning and explainable AI. We test several models including XGBoost, LightGBM, SVR, and staking Ansible. Shape was used to interpret future effects, and output was applied for hyperparameter tuning. The datasets include over 14,600 housing records enriched with spatial and socioeconomic features such as BIT distance, POI density, and neighborhood income. Let's take a close look at how the data was processed and features were engineered. Key features include spatial lag, BRT network-based distance, and land use mix. Feature selection was performed using shape, mutual information, and recursive elimination. The final model used 31 features, and the spatial correlation was confirmed with Moore's I at 0.47. After preparing the datasets, I tested multiple models to compare their performance. XGBoost achieved the best performance with an RMSE of 3,574 and an R-square of 0.832. LightGBM was the fastest to train but slightly less accuracy. The tracking model also performed well. SVR, however, showed weak performance overall. Once the best model was selected, I applied shape to interpret how each factor affects price. Using shape value, we found that BRT proximity had a nonlinear influence. Price peaked at around 300 meters from a station, but declined sharply within 50 meters, likely due to noise and congestion. District level difference also emerged. Xiamen districts show strong positive slope circles, while Xiamen shows almost none. The slope patterns are just analytical. They also suggest clear direction for urban policy. First, we observe spatial heterogeneity. Xiamen benefits most from BRT, while Xiamen shows little response. Second, GM validation for shape similarity shows hold positive effects at 300 meters, but negative within 50. Based on this, I identified 18.3 square kilometers of low-efficiency TOD zones. Refining the TOD boundary to 500 meters could boost land use efficiency by 23%. In summary, the current study makes a significant contribution to the field in terms of methodology, theory, and practice. However, it has three main limitations. First, the data ends before 2024. Second, it lacks real-time demand-side indicators. Third, some collinearity may affect ship attribution. Future work may integrate dynamic data, causal methods, and causality comparison. That could conclude my presentation. Thank you for your attention.